Yeah, on this, inductor stuff, you know, from what I can tell, I mean, it just makes sense. I mean, that it shouldn't work the way we're seeing it here. I mean, if you have a higher turns ratio, like a 1 to 10, you're going to have 100 times the inductance. Okay, if you have 100 times the inductance, that's going to um, increase your RC time constant by 100, because your RC time or LR time constant is L divided by R, and if R stays the same, you can just look at R equal to 1. Okay, well, you increase that inductance, it directly proportionally increases the time constant. So that suggests that, okay, you go from 50 milliamps, a 50 milliamp current would theoretically translate into 5 milliamps, because it's got so much longer of a time constant, that you'd expect the current to decrease, especially if the impedance is equal. But setting that aside for a moment, I mean, just because it's got 10 times the number of windings, that right there means there's 10 times the ampere turns. Okay, so if you're dealing with 50 milliamps on to charge it, that's your charging current, should be 10% of that on the discharge path under those conditions, because you got 10 times the inductance, you got 10 times the windings. Well, that's 1/10 the current will produce the same, electromotive force or whatever. So it does make sense to me that the current would drop going from smaller to bigger, and then going from bigger to smaller, it makes sense that it would increase by 10 times, like I said before, based on the inductance. Again, because the inductance is going to get, to be 1/100th what it originally was. So, so yeah, it makes sense it would have, half 0.5 amps, on this bottom side, but it also, decreases the charge constant by 100 times. So it makes sense that that would generate a higher voltage, because its time constant is smaller and it's going through the same 100 ohm resistor. So it makes sense this would generate a higher voltage across it. And in fact, if you multiply 0.5 amps times 100 ohms, well, that's 50 volts. Versus 5 milliamps times 100 ohms, well, guess what? That's like 5 volts, right? So well, no, it's like 0.5 volts rather. So yeah, you'd expect it to generate the low voltage on the high windings rate. And that's just because, look, it's got a finite amount of energy in it. And if you had an inductor that has more inductance in it, you would expect it to be easier to get, based on the 10 times the number of turns, you'd expect it to be easier, require less current to get that same amount of energy in the coil versus an inductor with a lower number of turns. You'd have to have a higher current, certainly in the same time frame to do it, to get the same amount of energy in there. Fucking router. But yeah, you'd expect that to be the case. That's why it would only require 5 milliamps, of current initially anyway to get it, going through. But you'd have to charge it up, of course. This fucking router is a piece of shit. But at any rate, yeah, you would expect, you'd kind of expect it to behave like I'm describing, because, with all things being equal, if they're 1-to-1, well, it'll take the same amount of time to remove that amount of energy through the same impedance as it took to put it in, right? But on the other hand, if your time constant is different, but your charge current is also different, the time constant may be lower, or is higher, when you're going up, it's taking longer to discharge it, but you're doing it at a lower current, so, anyway, you just kind of expect it to behave not unlike what we're seeing here, so I don't know. I mean, it's just really puzzling. Something, this fucking router. But, the thing is that, like with a Mazzilli driver or something like that, you're basically taking a small number of windings, sticking it through a TV flyback, small number of windings, you're storing a certain amount of energy through a pulse for a, a 260 FET, and then you're all of a sudden turning that off. Well, of course, that's, being induced into the high windings, turn count secondary and producing a high voltage at a low current. So, and that's more attractive for it to go that way versus to discharge through the FET when it's able to, but it will discharge through the FET if it's got no other choice. So, I don't know.
I will use the Arduino to create a fast PWM pulse that will change its value according to this potentiometer, as you can see now on the oscilloscope. We will see later how this pulse can change the output voltage of our circuit. I apply this pulse to some transistors that will be connected to the primary winding of the flyback transformer. And at the secondary we have to place a diode, a capacitor, and a small resistor as a load. Now I supply 12 volts at the input of this simple circuit, and look what happens. By changing the PWM signal, we can change the output voltage, just as with the buck or the boost converters from the past tutorials. We can get a pretty decent control of the output. I can easily set it to 5 volts, for example, using the potentiometer. But instead of the potentiometer, we could add a simple feedback, connected to the Arduino analog input, and set the voltage at a defined value, let's say 5 volts. And also the used coupled inductor doesn't have to be this big. A small one would do the job as well. As you can see, with this other one, we can still regulate the output. They could come in all sorts of shapes and sizes. So it's very simple to regulate DC voltage with this circuit. But not just that, we have a lot of other advantages using this setup. So let's start and see how this flyback converter works. It works kind of the same as the other converter, the buck boost DC to DC converter. In that video we have seen this configuration, and we saw that we must have the inductor to create a magnetic field and then collapse, and as a result push voltage to the other side of the circuit and by that regulate the output. But now we have this other setup, which is kind of the same, but instead of the inductor we have the transformer. But this will be used as a so-called coupled inductor. So first, let's see why this won't work as a transformer but as a coupled inductor. In a transformer, we push current to the first winding, and another current will pass to the secondary winding, and the load attached to that, and that's something basic. But in a coupled inductor, we will see later that because we have a diode at the secondary winding, when we push current to the first one, current won't be able to pass to the secondary winding. But that energy must go somewhere. Well, the energy will be stored in the core of the inductor, as a magnetic field, just as in case of the boost or the buck converter. Then, in the second stage of the voltage conversion, when we cut the current from the primary, the magnetic field created will collapse and push current in the opposite way in the secondary winding. That's why in this configuration our transformer acts as a coupled inductor. But if you look at the current and voltage values, the coupled inductor acts as a transformer, so we could have a gain, and the inductance ratio is given by this formula, where the N is the amount of turns of each winding. Okay, so let's get into more details. This is our circuit now. Here we have the coupled inductor with a 1-to-1 ratio, and the primary is connected to the power supply through a switch. The secondary also has a switch connected in order to disconnect the load when we need to. So let's say that we close the first switch and open the second switch. The secondary will now be in an open circuit, so no current could pass through that coil. So the energy will build up in the core of the coupled inductor. Then, in a very fast instant, we open switch 1 and we close switch 2. Now the magnetic field that built up will collapse and the current will now flow towards the dot of the secondary coil. So voltage drop will be created in this way. So we have reverse polarity. So we can use this reverse polarity voltage in order to get rid of the second switch. We know that the diode will let current pass only in one direction. So we change the second switch with the diode. And look what happens. In this case, when switch 1 is closed, it will create a voltage of this polarity on the primary. And that will create a voltage of this polarity on the secondary. So current will want to flow opposite to the diode. So by that, the current flow will be blocked. And that's exactly what the second switch was doing when it was open. At this stage, energy will be pushed into the core of the inductor, just as before. And now, when we open the first switch, the field will collapse. If the current in the primary was going into the dot like this, the current in the secondary will go into the dot like this. So now we have a current flow, and we have a voltage drop on the load in this direction. And that's how we get rid of the second switch using a diode. And to get a positive voltage, what we have to do is to invert the secondary coil, so now the dot will be placed at the bottom here, and also to invert the diode. So now we have a voltage at the output of this polarity. And if we also add a capacitor, we could smooth the output and store the voltage. And basically that's how the flyback converter works. We close the first switch and build up energy in the inductor core. Then we open the switch and the magnetic field will collapse, and the current will be induced in the secondary, and that will create a voltage drop at the output. The output voltage is given by this formula, where N is the ratio of turns of the windings, and D on and D off are the time periods where the switch is turned.
Okay. That's interesting. So I assume N is the turns ratio here. So if these were equal, that would be 1, and so V out equals N times V in, you know, but also times the duty cycle ratio, so you can actually change the voltage by changing this ratio here. So if let's see, these are proportional to each other, so you know, you can have like this 90% and this 10%. So you can end up with 0.9, so that'll produce a ratio. But you can also have an inverse, this being 10% and this 90%. So, well, at any rate, yeah, I can see. See, if its on time is higher than its off time, the voltage is going to raise. over Vn, whereas if it's the opposite, it's going to be a fraction of Vn.
Turn on or turn off. So as you can see, the bigger is the D on, the higher will be the output. This time period is given by the PWM signal that we have seen before, that will control the switch. But in our example, the switch will be a MOSFET, and connected like this to the primary winding. This is the schematic that I made for this experiment. The Arduino will control the D on and the D off time according to the potentiometer value. The PWM signal is applied to a small BJT transistor that will act as a MOSFET driver, and that is connected to the MOSFET gate. The MOSFET is our switch that will control the voltage to the primary coil. At the output of the secondary, we have a diode, a capacitor, and a load. And as we have seen before, we can regulate the output voltage. I have 12 volts connected at the input. The inductor in this case is a 1-to-1 ratio. That's why the output voltage will only go from the input value to lower values. But now I have this other transformer with bigger ratios. As you can see now, with the same 12 volts input, I could now reach voltages up to 20 volts. With the better main transformer, you could get any other values, according to the winding ratio and the D on and D off values. For example, let's see how this switched DC power supply works. We have the main input here of 230 volts AC. We pass that first to a fuse for safety. Then let's control the voltage to the primary coil. And the output of further value. The PWM signal is applied to a small BJT transistor that will act as a MOSFET driver, and that is connected to the MOSFET gate. The MOSFET is our switch that will control the voltage to the primary coil. At the output of the secondary, we have a diode, a capacitor, and a load. And as we have seen before, we can regulate the output voltage. I have 12 volts connected at the input. The inductor in this case is a 1-to-1 ratio. That's why the output voltage could only go from the input value to lower values. But now I have this other transformer with bigger ratios. As you can see now, with the same 12 volts input, I could now reach voltages up to 20 volts. With the better main transformer, you could get any other values, according to the winding ratio and the D on and D off values. For example, let's see how the switched DC power supply works. We have the main input here of 230 volts AC. We pass that first to a fuse for safety. Then we place a capacitor and a choke to block the higher frequencies. We can see these components on the schematic as well. And as you can see, we then pass the 230 volts to a full bridge rectifier. We can see 4 diodes on the power supply PCB as well, and that is our bridge rectifier. And together with this big capacitor of 400 volts, we rectify the voltage and we get a high DC voltage. Then we use these 2 transistors and a small circuit as switch 1 and switch 2 to make the transformer regulate the output at 12 volts. On the other side of the transformer, we have the capacitors, and that's how we get 12 volts DC from 230 volts AC. Be careful working with high voltages. So what advantages do we have? First, we have isolation between the input and the output, and that's very important for safety. As you can see, there is no direct connection between the primary and the secondary, so high voltage could be on one side and low voltage on the other side. For example, in a switch power supply like this one, the main input of 230 volts AC on one side and the output of 12 volts DC on the other side. Having a perfect isolation between these voltages is a very good safety feature. Another advantage is the use of multiple outputs. Remember at the beginning that we saw that one transformer had a lot of outputs, and that's because to the same primary inductor, we could add multiple secondary coils with a different winding ratio. In case of 2 outputs, the energy that builds in the primary will then divide for 2 outputs, and we could have different values at the output. We could even have one positive and one negative output, depending on the configuration. That's why switch power supplies with multiple outputs like this one here will have a big transformer with multiple windings. Another advantage is that we could use this as a boost or a buck converter, because depending on the winding ratio, we could increase or decrease the voltage or the both at the same time. A disadvantage of this converter is the output noise. Since we have a discontinuous current at the input and the output, that will create a ripple, and the output voltage will have noise. But that is common with all switch voltage converters, and we could just ignore that for everyday circuits. For more precise voltage values, you might want to look into other forms of regulating than switch supplies. So guys, that's how 5-back converter works. Be very careful if you work with high voltages as the small power supply, because that could hurt you. Take a look at the links below for more information. You could also find the schematic that I used with the Arduino and also the code that you need. I've also made the code and the schematic with the feedback, so check that out as well. And if you like this tutorial, consider subscribing and give a like to this video. So thank you very much for your support, to my patrons and to all my subscribers. Thanks again and see you later guys.
Okay.